Now, there is one more method which was developed by Magnel's method, and in Magnel's method, it is basically the en bloc region is actually considered as a deep beam with pre-stressing force as a load. For example, you see here in this case P naught is considered as a load. In addition to that, you also have some vertical loads that are acting on the system, which we call that as, let us say, V here, and we know that the end region is going to extend over a length of y naught, and these are your internal forces. M is your bending moment, H is your horizontal force, and V is your vertical force, and F is a vertical stress caused by the load, and FH is a horizontal stress that is caused by this pre-stressing and the load, and tau is your shear stress. So, if you look at this element, basically what we are trying to look at it, if I take the small element and we are trying to find out what would be the two normal stresses, which is FH and FV. In addition to that, you will also have shear like this. Okay, all these things are calculated, and then you find your principal compression and tension stress, just like we did in shear and torsion, right. So, anyway, so this you see here, this is the center line of the section, and this is your center line of your bearing plate. So, we know that P naught is going to be at the eccentricity E with respect to the CGC. So, this is your CGC, and this is your CGS, and this is your eccentricity of the applied pre-stressing force, right. In addition to that, at any section x that you are considering, you know what is the bending moment that it is acting, you know what is the shear that it is acting. So, if you move this P naught to the CG, then you know what is the horizontal compression force that you are putting. So, all those things effects are known. So, from there we can calculate what are the stresses. Now, what is vertical stress? The vertical stress will be the stress due to the vertical force and stress due to the moment, and we know that the stress, when the system is elastic, we know that the stresses can be calculated as a some constant times m by b h square, and similarly the stress due to the vertical force can be calculated as some constant times v by b h, right. And horizontal stress will be stress due to pre-stressing force plus stress due to the eccentricity of the applied pre-stressing, and this is a simple your stress concept that what we talked about. So, the stress is a horizontal concentric component is going to be P naught by P h, and eccentricity of the pre-stressing, it creates a moment of MP, which is P naught into E, and we are calculating stress at the location of your cable. So, and this is your I and this is your Y. So, you can get your FH. So, in this way I can get the vertical stress and the horizontal stress that what we are getting in an element, and the shear is basically K3 into again VBH some things. So, basically what we are trying to get here is I get, of course, you will have shear also. Okay. So, like this I am able to get my normal stresses, okay, on this element. Again, please note that this Fe is coming from the moment of the forces about the horizontal plane. It is not your bending moment, okay. It is basically you are taking the effect of your horizontal forces induced due to bending, but you are taking moment about the horizontal plane. So, that is the reason that we are taking Fe like this, and then you get your two stresses here in a Mohr circle, you get your 2 points, and then from your Mohr circle you can get your principal stresses as these two, right. Okay, probably I think the point is here sigma 2 and sigma 1, right. So, this is sigma 2 and this is sigma 1, right. So, you can calculate your principal stresses. The moment I get my principal stresses, I know where the cracking is going to happen. So, then I can put my reinforcement that is required for that, right. So, this is simple Mohr circle equation. You get your principal stresses as this, and principal and maximum principal and minimum principal stresses can be calculated like this, right, and the angle of your principal plane also can be calculated. So, we know that we have discussed extensively in the shear chapter and torsion chapter. So, the same thing applies, right. Now, how do we get the coefficient of stresses at the end block? Depending upon the distance from the far end where you are taking the section, already from elastic stress analysis, the K1, K2, K3 values are actually reported by Magnel, and that can be readily used to calculate your principal stresses. So, for example, if you look at it, if I am taking a distance 0.4 of your overall depth of the member, K1 is minus 4.32, K2 is 2.16 and K3 for shear it is 1.72, right. So, we can use them to calculate your Fe and Fh, tau also can be calculated, then I can get my principal stresses. Once principal stresses are then I know what are the kind of tension that is there and the orientation of the tension stress as well, and accordingly I can use them for designing the reinforcement. This is Magnel's method. Okay. Now, how does the IS code takes care of all this en bloc region design, right? So, in bearing stress is minimum of we take the bearing stress, there is a limit. It can never exceed 80% of your compressive strength of characteristic compression of the concrete. In addition to that, it is also should be 0.84 Ci times square root of ABR by A punching. So, what is ABR and A punching? ABR is the bearing area of concrete and A punching is the punching area of concrete. We can see that in the next slides. Now, FCA is if you are transferring the force at a certain strength before FCK is developed, then you take that stress during which you transfer the pre-stress. So, this is the cube strength of concrete at the time of transfer, right. Now, you see here what is the punching area? This is the bearing plate width. So, we say Yp naught and Yp naught, the total width of the plate we take it as 2 Yp naught. So, punching area will become 2 Yp naught times 2 Yp naught. Now, if you are putting a circular plate, we have to convert this into a square plate to calculate your punching area. Now, inside the concrete, it is going to develop like a frustum. Okay. So, this is just at the anchor plate, what are the bearing area, but inside also a concrete you are putting a lot of reinforcement. So, it is going to develop over a larger area. So, that is why we say that as a concrete will act like a frustum and it will develop that area is called bearing area. So, you can see here that bearing area. Typically, we take let us say from this plate you take this maximum edge distance, if you take that as y naught, bearing dimension will become like this, from here to here is y naught and here it is y naught. The same this side also you go and it becomes bearing area 2 into y naught into 2 into y naught. So, bearing area will be much higher than that of your punching area, right. So, the reason is we imagine that concrete behind the bearing plate is going to develop like a frustum and a larger area will help me in resisting this applied huge compression. So, that is why this bearing area taken at a higher value. There is going to be a dispersion of the stresses, right. So, that is why this bearing area taken to be higher than your punching areas. Now, what is the bursting tensile force on the concrete? I need to use that for design, right. The code gives you a very simple expression. Bursting tensile force is taken as 0.32 minus 0.3 into Yp naught by Y naught for particular P naught. P naught is the load in the tendon and Yp naught is the side of the bearing plate and Y naught is the side of the end block and FBST is the bursting tensile force. Now, what is the stress? Now, I know the stress, I know the force FBST that is given and that has to be resisted by some stress in the steel times the area of the steel, right. So, I can calculate now if I assume Fs to be 0.87 Fi which is the yielding stress, then I can quickly calculate my area of the steel that is required. Okay. If the stress is limited to 0.87 times the yield strength and if the cover is less than 50 millimeter, the strain in the rebar again should be limited to 0.001. So, this is this okay. So, the maximum we can take 0.87 Fi, but if the cover is less than 50 millimeter, the strain in the rebar is limited to 0.001. That means, the Fs will be less than Fi. Okay. So, the steel would not have yielded. So, that means I have to take lesser stress. So, the code is indirectly saying that the cover may give away. So, you have to limit your stress in the steel. So, you have or indirectly the code is asking you to put more transverse reinforcement to take care of that. Okay. Hence, the area of the steel required in the end zone can be written as if let us say cover is more than 50 millimeter, then the area of steel is FBST divided by 0.87 times Fi. Okay. So, let us see. So, now how do we put the reinforcement? So, this is what we said. Close to the bearing plate, on the top here you have spalling region, to resist the spalling. Sometimes in the end block region people also use fiber reinforced concrete, and we know that the fibers, especially if it is reinforced with steel fibers, they are very effective in arresting the crack, and they are very helpful in limiting the tension stresses, and you can optimize the end block design quite well. And so, in the bursting region again, and where is the bursting region? Again we said up to 0.1 times your Y0, it is a compression region. This is the compression region, but this is the region that is actually in tension, right? This is in tension. So, this is the region where we need to put lot of this transverse reinforcement to take care of the bursting tension force, right? Now, the area of the steel at the end zone should be provided in the bursting region, that is at a distance of 0.1 Y0 from the end. So, typically we end up providing this kind of a mat type reinforcement, and both in the horizontal and vertical direction, though we know that transverse tension is going to create like this. Actually, this steel is more effective, we know that, right, but we also put a little bit of horizontal reinforcement to confine the concrete really well. Okay. So, that is the reason we provide this kind of a mat. In fact, at the end you always also put some kind of a U type, like a staple kind of reinforcement. It is provided to confine the concrete just behind the bearing plate. Okay. Now, let us go through an example and see how do we take care of this. Okay. So, let us say we have 300 mm by 600 mm section, and I have prestressing cable at a distance of 125 millimeter, and this is your effective cover, and the prestressing force is 1000 kilonewton, and my bearing plate I am taking it as 150 mm diameter plate. The diameter of the duct is 50 millimeter, and compressive strength of the concrete at transfer is 40 megapascal, and yield strength of the steel is taken as 500 megapascal, and design is going to be as per IS 1343/2012. Now, if you see here, in this case 300 mm by 600 mm, and this is the given section. Now, what would be the bearing area? You see here, this is 125 millimeter. The area of the circular bearing plate is this 17,672 millimeter square. The equivalent size of square plate is going to be 132, right. So, if you see that equivalent square plate, is going to be 132 by 132, right. So, this is basically square root of 17,672 becomes 132. Now, what is the size of the bearing area? We have seen that it is going to be 2 Y0. So, which is basically 2 into 125 is 250 mm is the size of the bearing area, right. So, that is the reason the width of the section is this, right. So, this is 250 mm, and then bearing area is this, size of the bearing area is 2 into Y0. So, basically 250 mm by this. Now, what is the punching area? Punching area will be just the size of the square plate, which is 132.9 into 132.9. So, this is the same, and bearing area is basically 250, the entire 250 by 250 minus this area of the duct, which is this. So, basically this. Now, how do we get the bearing area? As we have seen, punching area will be small, bearing area will be high. Now, how do we get the bearing area? So, basically you go back, this is 125 mm, and then you double it. Now, this side also you will get the entire area as your punching area, because now the concrete is basically going to act like a frustum. If you see the allowable bearing in the concrete area, then 0.48 times FCI times square root of ABR by A punching is this 35.4 megapascal. So, area of the bearing is 60,536, basically 250 by 250 minus pi by 4 this d. This is the duct area, right. And then applied bearing stress will be, this will be actually 10 to the power of 3. So, you see that it is 16.5 megapascal, which is less than 35.54 megapascal, which is, this is allowable bearing stress as per the code, 0.48 FCI into square root of ABR by A punching. and applied bearing stress is this divided by the bearing area, which gives me this. So, it is safe, and bursting tension force is as per the code is P naught into 0.32 minus 0.3 into y P naught by y naught. So, you get a force of about 160.52 kilonewton, and reinforcement is FPST divided by 0.87 into Fi. So, which gives a area of 369 mm square. So, for that we say that okay, you go ahead and provide 10 mm diameter rebar for end zone reinforcement. So, 6 10 mm bar if you provide, it will be good enough. Okay. So, basically we go ahead and put in the transverse direction, same can be provided in the horizontal direction to actually confine the area. But actually for bursting tension you put only this vertical like a stirrup. This should be in addition to whatever that shear reinforcement requirement is suggesting, right. So, I think the example is okay. Now, let us conclude. So, basically in this lecture we have understood the mechanism of transferring the pre-stressing force in a post tension member, right, and we also looked at how the transverse tensile stresses are developed for different bearing plate configurations. We have seen that increase for the same pre-stressing force, if you provide multiple number of bearing plates, then your length of your end zone is going to come down and you are going to have more economical design. And we also did one example of an end zone region with an example, right. So, with that we are completing this second part of the module of checking for the end zone design for a post tension system, and we will continue with the new module in the next week. Thank you.